In the previous video, I showed you a demonstration to illustrate the static friction force. The static friction force acts in situations where there is not yet sliding motion between two objects with surfaces in contact. Static friction acts so as to keep the sliding motion from ever getting started in the first place. This figure depicts a situation where static friction is acting. We have a tension force trying to pull a box to the right. However, the box does not begin moving to the right because we have an equally strong static friction force pushing in the other direction to cancel out the pull of the tension. As we saw in the previous video, even if the strength of the tension force were to increase, the strength of the static friction force would increase as well, keeping the box in place up to the point where the strength of the static friction force was maxed out. Because we know that static friction can max out, we can say that the magnitude of the static friction force in a particular situation lies between 0 and some maximum value. I'm going to express that last statement as an equation. So let's say that F sub s represents the magnitude of the static friction force. The magnitude of the static friction force must be at least 0 because the magnitude of any vector is always at least 0. And the magnitude of the static friction force must be less than or equal to some maximum value, which I will call Fs max. So this Fs max here represents the maximum possible value of the static friction force. It turns out that the maximum strength of the static friction force is directly proportional to the strength of the normal force. So I can say then that the maximum strength of the static frictional force is directly proportional to the strength of the normal force. We never really like to be writing proportionality relations if we don't have to. We would rather write an equation, and the way we go from a proportionality relation to an equation is to introduce a proportionality constant. In this case, the proportionality constant we introduce is what's called the coefficient of static friction. So the symbol here is the Greek letter mu, followed by an S subscript for static. So this is called the coefficient of static friction. So we have then that the maximum possible strength of the static friction force equals the coefficient of static friction multiplied by the strength of the normal force. Now, it's important to understand that most of the time, the actual strength of the static friction force is not equal to its maximum value. Usually, we can say that the actual strength of the static friction force is not equal to the maximum possible value. Or in other words, we can say that usually the actual strength of the static friction force is not equal to the coefficient of static friction multiplied by the strength of the normal force. All right. So when is the actual strength of the static friction force actually equal to this maximum value, mu s times n? The actual strength of the static friction force is only equal to this maximum value when static friction has been maxed out. In other words, the actual strength of the static friction force is only equal to this maximum value when the object is just on the verge of slipping. Okay, so we can say then that the actual strength of the static friction force takes on this maximum possible value, mu s times n, only when the object is on the verge of slipping. Most of the time, the static friction force is not maxed out, which means that most of the time, the actual strength of the static friction force is less than this maximum value. Okay, so in the next video, we will do an example problem involving the static frictional force.